not too interested in that mystery, but it's still a mystery. The other things we didn't expect were soil, pH. We measured the soil pH. It was the first measurement of pH. Took soil, add water, stick a pH reader in. Very simple. It's the first time we'd ever done it. We sort of expected the soil to be acid. We expected it to be acid because of the jarosite discovered by the rovers at the equatorial sites. Jarosite is an iron mineral, iron-sulfur mineral that only forms at a pH of 3. And they found it at Meridiani. There's a big to-do about it. Oh, jarosite found on Mars. The whole planet must have been acid. So there's all these papers about Mars was an acid world, full of acid and on acid and whatever. But we measure, the first measurement we actually do, the pH is 8, basic, and buffered by carbon. It's kind of funny, ironically funny. But the big surprise, and to my mind, the big result for the Phoenix mission is the discovery of perchlorate in the soil. It just completely blows us away. And that's why TIGA didn't work. And I'm going to come back to that. Perchlorate is now my favorite molecule. A year and a half ago, I didn't even know what it was. Now it's my favorite molecule. And I'm now the self-appointed president of the perchlorate club. We study perchlorate. There are more projects dealing with perchlorate now than you can imagine. There were other results. We did not detect organics or nitrates with the TIGA instrument. But it turns out the TIGA instrument didn't work because the perchlorate did not cause the TIGA instrument not to work. Another interesting result was we found a type of ice that we didn't expect, so-called segregated ice. And here it is. So we're digging down, we dig down through dry ground as expected, and we hit this layer of hard ice-cemented ground, just as expected. And it's dark because it's 50% ice, 50% dirt. But then we also saw white stuff that we did not expect. So what is the white stuff? It could be ice, it could be carbonate, chalk, or it could be salt. So we watched it for a few days, and it started evaporating. So that rules out chalk and salt. We knew it was ice. We weren't expecting that. Discrete, relatively pure ice lenses like that were not what we were expecting. We were expecting ice-cemented dirt. On Earth, when we see segregated ice like this, it requires a liquid phase to form. So on Mars, we think it might be indicative of a liquid form. Some people said, well, maybe it's just buried snow. And other people have said, well, maybe it's vapor deposited in ways that we don't quite understand. So we're not sure what the significance of that ice is. What we certainly found is segregated ice, unexpected and still unexplained. But perchlorate was the big news. Perchlorate is a type of, is a chlorine molecule. It's a state of chlorine in which chlorine is at its most high oxidation number, +7. So it is the most oxidized form of chlorine. It is not the most reactive. It is not what you put in your laundry to bleach your clothes. That is hypochlorite. So it's a difference between oxidized and oxidizing. Hypochlorite is very oxidizing. It's very reactive. Perchlorate is not. At room temperature, it just sits there. I've got 3 jars of it sitting in my office. It just sits there. It's very, very stable. Looks like salt. But it's the most oxidized form of chlorine. And if you heat it up to 350 degrees, it explodes. Right? Which is why it's very good for use in solid rockets. The shuttle and the Ariane 5 both use solid rocket boosters that are ammonium perchlorate. It's very easy to handle. At room temperature, it's very stable. Cut it with a knife and machine it and put it in the form you want. But if you then heat it up to 350 degrees, it explodes. And the explosion just propagates up the stack, which is why a solid rocket motor, once you turn it on, you can't turn it off. It's really just an explosion propagating up the stack. And it's ammonium perchlorate. That's why it's used in rockets. It's used by the military in missiles. And when it's decomposing, it releases oxygen. Hot oxygen comes out. Needless to say, if you have any organics near it, it reacts. Think of it as super hot reactive bleach. This is not the sort of thing you put into a thermal evolve gas amyloid. T got heated up the soil to 500 or 600 degrees. It's 1% perchlorate. I think we're lucky the spacecraft didn't blow up. It did bad things to the inside of the instrument. It destroyed the nickel coating on the wall. It generated plugs in the plumbing. It's just generally a mess. And if there was any organics in there, it would have been destroyed anyway. Perchlorate is also a very strong antifreeze. You guys probably put sodium chloride out on the roads here. Further north, you have to put calcium chloride out on the roads. It's got a lower eutectic, right? Perchlorate's got a really low eutectic. It can create a solution of liquid water down to -70 centigrade. That's very interesting because that would allow liquid water on Mars even at current temperatures, saturated solutions. Could explain that segregated ice. But finally, from an astrobiology point of view, perchlorate tastes good. Organisms eat it. It tastes almost as good as nitrate. Don't eat, this isn't literal. Don't go home and taste perchlorate. It's actually bad for your thyroid. But it is a terminal electron acceptor consumed by some bacteria, and it has about the same efficiency for oxidizing, say, organic material as nitrate does. And there's organisms that eat perchlorate. So when it was first discovered, the press said, oh, rocket fuel on Mars, that can't be good for life. But quite the opposite. It is quite good for life, as I'll come back to later. And so the antifreeze properties of perchlorate are interesting. Here is the maximum temperature recorded at the Phoenix site, -30. Here is the minimum temperature, -80. Well, that temperature range does not cycle through the melting point of ice, obviously, which is 0. But it does cycle through the melting point of perchlorate solutions, as well as other saturated solutions too. So liquid water at the Phoenix site wouldn't be possible if it was pure water, but it would be possible to have liquids that were saturated salt solutions going between solid and liquid phase. And that could be the explanation of the segregated ice we see. So this ice may be formed not by, may have formed from a liquid phase, but from a liquid phase that's a brine rather than pure water. We don't know that for sure. What I want to do now